Hello, yeah, I'm back with some more waves questions. We're starting here with describe in terms of vibrations the difference between a longitudinal and a transverse wave. Give one example of each wave, right? So they want us to do it in terms of vibration, so we want to use that word in there. So for longitudinal then, let's say that the vibrations of the wave, or the medium vibrations of the medium of the wave, that sounds quite good, doesn't it, are parallel in this case, because we're doing longitude, parallel to the direction of travel of the wave. Direction of travel of the wave. And an example of that would be, so sound waves, e.g. sound waves. Then we've got the transverse. So for transverse, we're going to say much the same, but we're going to say the vibrations of the medium of the wave are perpendicular to the direction of travel of the wave. So we're writing out exactly the same stuff. We just change parallel to perpendicular. And then we'll say, e.g. electromagnetic waves. Figure 6.1 shows a loudspeaker fixed near the end of a tube of length 0.6 meters. The far end of the tube is closed. The frequency of the sound emitted from the loudspeaker is increased from 0. Now, a particular frequency of stationary wave is set up in the tube, and the sound heard is much louder. Explain how a stationary wave is formed in the tube. Right, yep, same stuff. So, incident wave that travels along the tube is reflected at the closed end of the tube. The reflected wave and the incident wave superpose, producing a resultant wave of nodes and antinodes. I've written that out so many times that I'm not going to do it here. So that's that one. But you've got those three steps as usual. Figures 6.2 and 6.3 show stationary wave patterns of amplitude against position along the tube at the fundamental frequency and the next possible harmonic at 3 times the fundamental frequency. Right, yeah, and we have to have this set up because at the open end of the tube we have to have an antinode, and at the closed end we have to have a node. So if you're going to keep that set up, then that's clearly going to be your fundamental, and then the next one up is going to have to be this. Describe the motion of the air in the tube containing the stationary wave. Right, so one for each tube then at 0 meters, 0.2, 0.6. Right, so for figure 6.2, so at 0 meters, this is where we've got, so we want to say that they're oscillating at maximum amplitude because it's an antinode. And so we want to describe the whole motion of the air. So we're saying it's oscillating a lot, and we also want to say that it is along direction, along length of tube. It's probably best, along the length of the tube, or the direction of oscillation. Let's go with that. Direction of oscillation. Oscillation is along the length of the tube. So just to make sure that you're making it clear, you know this is a longitudinal wave and that's the direction that things are moving in, rather than it being transverse. So that's at 0 meters. Then we have to say at 0.2 meters, well, it's the same but smaller amplitude. Same except smaller amplitude. And then at 0.6 meters, we're going to have no oscillation because it's at a node. Right, now for 6.3, we're going to have, right, so at 0 meters, we're getting same thing, much the same as we had here. We're going to get the oscillation at maximum amplitude along direction, direction of the tube. We've got the same as what we said here, except we're also going to put at 3 times frequency of figure 6.2. So otherwise it's exactly the same as we've got in the first part. They're both antinodes. So they're both oscillating the same way. They've got the same direction of oscillation, the same amplitude of oscillation. The only difference is we've got this 3 times the frequency. So that's the bit that you want to put in. You can write out the same stuff again, or just say it's the same as 0 meters for 6.2 plus it's got this additional increase in frequency. Right, at 0.2 meters, that's where we're going to be getting no oscillation because we've got a node here. And then at 0.4, now they've changed. Right, so at 0.4 meters, that is going to be same as 0 meters, but anti-phase. Because when one of them's going up at 0 meters, it's going up here, it's going down here, and vice versa. So yeah, we got anti-phase, but the same sort of motion. Right, that was a nice bit of descriptive work to do there. Part D. The end of the tube at 0.6 meters from the loudspeaker is now opened. Right, so I made it double open tube. On figure 6.4, sketch the stationary wave pattern of amplitude against position along the tube at a new fundamental frequency. Right, so now we need to have antinodes at both ends. So we're going to have a node in the middle, and we're going to have something that's going like this. And then we can draw in the dotted bit to make the envelope. State how the frequency of this stationary wave is related to the frequency F0 of figure 6.2. Right, well now what have we done? We've halved the wavelength, so we must have doubled the frequency, because we've got that is a half, because now we can see we've got here we've got a quarter of a wavelength, here we got half a wavelength in the same amount. So we've halved the wavelength overall. So that means that we're going to have the frequency is multiplied by 2. All right, because we've got the same, they're moving at the same speed that we've got on all of this. Right, okay, that was good. So I've got one more question to do on this block. Right, both electromagnetic waves and sound waves can be reflected. State 2 other wave phenomena that apply to both of these types of waves. Well, we can say diffraction and refraction. So diffraction, refraction. Just have to state them so we don't need anything else. Explain why electromagnetic waves can be polarized but sound waves cannot be polarized. Right, so only transverse waves can be polarized. Transverse waves can be polarized. And then say that EM waves are transverse, sound are longitudinal. Sound longitudinal. Describe briefly an experiment to demonstrate the polarization of microwaves in the laboratory. Right, so we're going to want to say, we want to place, let's go through in steps. You want to place the equipment out. So let's place a transmitter and a receiver facing each other. So that's at least got our setup. Then we want to say, oh, actually, we're going to need polarizers, aren't we? And let's have 2 polarizing filters in between. Then we can say rotate. I'm going to run out of space here, so I'm probably not going to write all of this out. But we want to say rotate one filter from parallel to perpendicular. And then observe the signal will go from a maximum to 0. So that's the received signal. So maybe put received signal in there. Received signal will go from a maximum down to the 0 as you're rotating those. I mean, you might even want to put in some explanation of why. It doesn't seem to say that you necessarily have to do that, but if you've got time in an exam, it doesn't hurt to say that once the sound has gone through the the microwaves have gone through the polarizing filter, then you can say, well, all of the microwaves are polarized vertically, and then when the second filter is aligned horizontally, no transmission is going to occur. So maybe you want to add that in. I don't think really you need it in the way the question is set up. You just want to say what equipment you've got, transmitter, receiver, and 2 filters. What you're doing to the filters, rotating one of them from parallel to perpendicular, and then what you expect to observe, as in the signal is going to go from a maximum to 0. Right, a sound wave emitted by a loudspeaker consists of a single frequency. Figure 4.1 shows a displacement against time graph of the air. Right, find the amplitude of the air motion. Right, the amplitude is our maximum displacement. What does that look like? It looks like 0.3 millimeters, doesn't it? Just reading it off the graph. The frequency. So frequency, I really haven't put these time labels very well. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, I think they've got that cut in. So the period is 2 milliseconds. So the frequency is 1 over the period. So that's going to, oh no, that's only half the wavelength. So it's going to be at 4 milliseconds. Yeah, just double checking that. Period is 4 milliseconds. Yeah, nearly fell into the trap of just marking out the lines and then only doing half of the wavelength. Right, so where was I? Yeah, the period is 4 milliseconds. So the frequency is going to be 1 over 4 milliseconds. So it's like 250 hertz when you put that through the calculation. Right, the sound generator is adjusted so the loudspeaker emits a sound at the original frequency plus twice the intensity. Sketch a new displacement against time. Explain your reasoning. So intensity is proportional to amplitude squared. So if the intensity is times 2, then the amplitude is times √2 in order to keep that proportionality. So we need to increase the amplitude. Is going to be going up from, what do we have? We had 3. So 3 times, well, 0.3, but we can take that off. So 0.3 times, say, 1.4 is going to be equal to 0.42. We're at the same frequency. So we're still going to be going through, I mean, again, it's so hard to tell where the points are in all of this. Let's say those are the, I mean, who knows? It's really hard to tell with these lines. Actually, it doesn't look particularly even, does it? But still, I don't really know what I'm going to do about this. So it's going up to there, and then down to there, and up. So you're wanting to keep the same frequency. So wherever these have cut, you want these to cut in the same place. Okay, it looks like I missed the last one there. But you get the idea. We want the same number of oscillations in this period, as in we've got 3 peaks, 2 troughs, cutting the axis the same number of times. But we want the amplitude to have gone up from 0.3 to 0.42. Suggest with reasons the apparatus you would choose to detect and measure the frequency of the sound wave at P. Right, so we just want to measure frequency of a sound wave. So we're going to need a microphone because we're going to need some way of getting sound to electrical signal. So I suppose that's the reasons that we're talking about here, electrical signal. And then we're going to want some way of looking at or measuring that signal. So we're going to want an oscilloscope, because that's the thing that we look at, to look at oscillations. So we'll have an oscilloscope to display the oscillation for measurement. Display oscillation for measurement. So yeah, really run out of space there as usual, but you know, you get the drift. So yeah, another couple of nice questions. I'm quite enjoying these waves ones at the moment. But yeah, you'll see they like these redrawing things in waves questions, and a lot of it is marking in these fixed points. Okay, it's difficult on here with how badly the labels on the x-axis have been set up, and it's easier on a bit of paper. But if you mark on those key points, thinking, right, okay, we still need these intersections, we still need these peaks and troughs, but we've got a new amplitude, then it helps you keep that same frequency going on without changing the frequency, but just changing the amplitude. So marking on these fixed points and then doing a join the dots is definitely the way to go about it. Right, so that's finished another bunch. think we're about halfway through all of the waves questions now.